Thank you. Good morning. First, I'd like to thank the organizer for inviting me. It's a very, very beautiful place, and I enjoyed very much, and I enjoyed this conference. And second, I would say that my task is much easier because Juraj showed all these details in his perfect talk. So I will, in many aspects, I will somehow cite his talk. And then I'd like to announce the poster by Ondřej Sahat today or tomorrow. Today is the poster session. He will explain the details of X-ray standing waves. So this is our collaboration. Myself, Juraj, Ondřej, and yeah, this is Czech-Slovak company, and I must say in that company I am the most skeptical one. And Juraj, as maybe you recognize, is the less skeptical or most optimistic. Somebody must be optimistic, otherwise it wouldn't work.
Much worse.
Yeah, yeah. Anyway, I think I can skip these pictures you've seen in many times. And I will just remind you that what you saw before 1 minute ago, a few minutes ago, there is a static polling of, or static change of polling of Rashba semiconductor germanium telluride caused by X-rays, by hard X-rays with the energy of 11 kilovolts. So the frequency is very, very high. And in spite of that, the effect is static or very slow. So this was our puzzle. How is it possible such a fast changing field can cause a static effect? So in my talk, I will concentrate myself more or less to two technical issues: how to calculate the OM wave. I will show which quantities could give rise to this static polling effect without any physical details, but I will not consider the true physical mechanism. So there is no physics in my talk. This is just a techniques. This is just a technical issues, how to calculate it. Yeah. So the outline. So first, something about high X-ray. Probably you know, but in case that somebody doesn't remember, the hard X-rays, the wavelength of hard X-rays is roughly 12.4 divided by energy in kilo electron volt. So we are using typically 11 kilo electron volt. So the wavelength is around 1 angstrom, which is comparable to atomic distance. Concerning the refraction index, maybe you remember from textbook that the refraction index for hard X-ray is less than unity. The difference between 1 and refraction index is something like 10 to minus 5, the real part. The imaginary part is 10 to minus 6, and this difference decreases with increasing energy. These are the absorption edges. Concerning the penetration depth, the penetration depth increases with energy is, as you can see, is a couple of microns, around 10, 15 microns for tungsten. So if we want to make a pure faceplate, just by phase shift due to refraction effect in the material, the faceplate should be thin in the thickness of something like 10 to 100 microns. So very thin faceplate. But we are not using faceplate, we are using zone planes, and the spiral zone plate is simply the transmittivity of such a spiral zone plate is spiral-like. That means it depends on the ion quantum number, azimuthal angle phi, and radial distance. K is simply 2 pi over lambda, this wave vector, and r is the radial distance. So these are the zone plates. I think you have seen this picture many times, so I can skip it. And my task in this small company of collaborators was to calculate the OM field. And because I'm not from this community, I'm going from another community, I have no much experience with this. So I did it maybe using the worst possible method, namely brute force. So I took simply standard Huygens-Fresnel diffraction integral like this. This is the transmittivity of the zone plane. This is the inclination factor. You know it from the textbook. And I did it by brute force. That means I did it exactly. And the only approximation was that the inclination factor is 1. That means the angle between the incoming beam and diffracted beam or transmitted beam through the zone plane is small, and so the inclination is 1. So this is the only approximation that I used. Since I want to calculate the diffraction, it is always easy to, or it is always good to decompose the wave field into a superposition of plane waves. And this is done simply by this Fourier integral. But what is important, if we want to make the decomposition to plane waves, we have to integrate over the in-plane component of the wave vectors. The vertical component is simply due to the elasticity of the scattering. But we have to take into account also the evanescent wave with imaginary kz. All these kx and ky value must be taken into account also outside the, I would say, Ewald circle. And if we do it, if we calculate if we take this Huygens-Fresnel integral and do this Fourier transformation, we find that there is a quite simple expression for the wave behind the zone plane. Simply superposition of the waves, and the amplitude of each wave plane component is proportional to the Fourier transformation of the transmittivity of the zone plane divided by kz, which might be imaginary, of course. Yeah, but this is only the scalar wave, and of course the wave is vectorial, and the polarization or the direction of the E wave can be determined from the Gauss law, namely that the divergence of E is 0 because there are no free charges. And from that, it follows that depending on the polarization of the incident wave, we can write the wave behind the zone plate using this expression, which is again a Fourier integral with the Fourier transformation of the transmittivity of the zone plate times some vector function. And the vector function depends on the polarization of the incoming wave. This is written here. This is the Ws is the vector function, and you can see this is for the for the x-polarized, linearly polarized along x, linearly polarized along y, and circularly polarized wave. So the only difference is in this vectorial function. The remaining part of the integral is the same. So the crucial point is to calculate the Fourier transformation of the transmittivity, and this can be done numerically. These are the results. Maybe there is an analytical formula for the spiral zone plane, for the Fourier transformation of spiral zone plane, but I don't know. But I did it in this brute force way. These are the results. So I think I can skip these pictures. We have always the amplitudes and phases. For the non-OM wave, linearly polarized, I always used, as I said, 11 kilo-electron volt as an energy. The focal distance was 10 centimeter, and the radius of the zone plate was 50 microns, so pretty small zone plate. So this is the this is in xy plane perpendicular to the propagation direction. This is in xz plane, that means along the propagation direction. Here you can see, here you can see the focus, the maximum of the intensity. This is again the phase. This is for circularly polarized light. This is for OM wave, linearly polarized. XZ, again, we have the focus, and we have the minimum in the middle. OM wave, circularly polarized. I think I can skip this. just for comparison, if we use a faceplate instead of zone plate, the main difference is that the faceplate is not focusing. So I think I can skip the details. Again, we can use the same formalism for the faceplate. The only difference is the Fourier transformation of the transmittivity of the faceplate can be calculated. This is a simply integral from the Bessel function. Well, L is the OM quantum number. So these are the. So as you can see here, there is no focusing. There is no focusing, and this is XZ plane. So there is no maximum of the intensity. Again. As I said at the beginning, it was a big puzzle for us. How is it possible that a static Pauling is caused by the harmonic field with high frequency? And thanks to long Zoom discussion with Konstantin, we understood that we have to take into account the second order quantities which have non-zero the time average. And there are several quantities of this type. For instance, Poynting vector. I would rather say Umov Poynting vector, maybe. I remember when I studied in 70s, it was in communist time, we had to say Umov vector at that time. Yes. Now it is Poynting vector, maybe it will be again Umov vector, I don't know. Maybe. Okay, so this is the time average Umov Poynting vector. It can be again expressed in terms of the Fourier transformation or in terms of superposition of plane waves, and this is the rotation of E vector. This is this, but of course, then the next step must be done numerically. Of course, there is no way how to do it because there is second order quantity. Another second order quantity which has no zero mean is the density of angular momentum, which is simply, as Konstantin showed in his beautiful talk, R times Poynting vector. And I calculated again the Poynting vector and the density of angular momentum in XY plane for non-OIM, XZ plane for non-OIM, XY plane non-OIM but circular polarized. This is with OIM. What is interesting, if we have linearly polarized light and an orbital momentum 1, then we have this distribution of Z component of the orbital momentum, and this is similar. This is similar to that. Yeah, the shape is the distribution of the MZ component, the Z component of the orbital momentum density is the same or similar, even if orbital moment is 0. Oh, sorry, I have to go another way. Then, after a long discussion with Juraj and other colleagues, I realized that maybe the Poynting vector or orbital momentum density is not the suitable quantity. And then we concentrated ourselves to second order polarization. And for the second order polarization, we use this formula that Juraj showed in his talk. This is a second order susceptibility tensor times E squared roughly, but since this is E squared, we have to take a real part of E, of course. So this can be written in this way. J and M are X, Y, or Z. And of course, we don't know the values of this second order polarizability tensor, but from the symmetry consideration, it follows that for the point groups C3V, which is the third order rotation axis, and the vertical mirror planes, which describes the symmetry of 1, 1, 1 plane of germanium telluride, the second order susceptibility tensor should have these non-zero components. And if we restrict ourselves to the calculation of the vertical component of the second order polarization, that means component along the threefold axis, that means component perpendicular to the surface, then we find that that this third component of the polarization vector has two contributions, a strong contribution and weak contribution, where alpha I is the incidence angle. This is our experiment. This is the germanium telluride sample. This is the threefold axis. This is the incoming beam. And this angle is simply more or less the Bragg angle for the 1-1-1 diffraction from germanium telluride. So as you can see, the P3 component, which should be responsible to the vertical poling of the germanium telluride, contains two contributions, strong one and weak one. Since we don't know the values of this component of the susceptibility tensor, simply put it 1 or 0 just to see how it behaves. So this is if we take only the weak component, that means only this one, then we have this distribution. This is the distribution of the P3 vector, that means the vertical component of the polarization in the xy plane perpendicular to the incoming beam. So this plane is in fact inclined by 9 something degrees to the vertical plane. So we have the weak component for non-OIM. As you can see here is OIM 0. And with OIM, this is this rotation pattern that Juraj mentioned already. You can see that depending on the position of the xy plane with respect to the focus of the zone plane, this is in focus, this is in front of the focus, this is behind the focus. The values of the displacement is in millimeters, is 0, this is 1 millimeter behind the focus, so it's just quite tiny. So this is the weak component. If we have OIM -1, then the rotation is opposite, of course. If we have OIM 2, the pattern is more complicated. There are some rotation, the pattern changes. This butterfly shape pattern somehow changes, making such a swirl, or how to call it. If we calculate, if we consider only the strong component, nothing happens. This is boring. This is just a maximum or annular-like distribution in the xy plane. So our idea was to calculate the rotation angle of these circular segments. So here are the circular segments 1, 2, 3, and we calculate the rotation angle as a function of displacement in front or behind the focus. And as you can see, the largest rotation angle belongs to the segment number 1. This is the closest to the focal, to the optical axis, and the rotation can make up to 25 degrees. So this is some spiral-like rotation of this P3 pattern. Yeah, the second, how much time I have?
2 minutes.
2 minutes. Okay. Dynamical diffraction of OIM. So we benefit from the idea that we can decompose the OIM wave to the plane waves, and we calculate the dynamical diffraction for each plane wave component and make this composition again. This is quite simple. This is the incoming beam. This is the sample. This is diffracted beam, and there was a detector window with a 2D detector. And maybe just to remind you, the very basic from dynamical diffraction, the diffracted intensity as a function of angular deviation from the Bragg condition exhibits this Darwin curve. This asymmetry is called by something which is called Bormann effect, and this Bormann effect depends on the imaginary part of the susceptibility. And what is interesting, if we take 1-1-1 diffraction using this 11 keV, both polarization S and P make almost no difference because the linear polarization factor is almost 1 in P polarization. That means in for this 1-1-1, diffraction is more or less independent from the polarization of the incoming beam, while for 5-5-5, for instance, the p polarization, the reflectivity of p polarization is by 1 order of magnitude smaller. That means this higher order diffraction acts as a polarization filter. Oops. Yeah, these are the formulas. So the idea was to decompose the ORM wave into plane waves, to calculate the dynamical diffraction for each plane wave component separately, and make the Fourier integral again. These are the formulas. Of course, each plane component must be decomposed into S and P component and do it separately and then make a coherent superposition of this ES and P component and make again the backwards Fourier transformation. And these are the results. This is a simulation of the detector image. So this is a simulated video. This is the detector image for rotating sample. So we are rotating the sample. We are changing the angular deviation from the break position. And this is the for non-ORM. So this is non-ORM. This is non-ORM, but behind the focus. And this is ORM. As you can see, roughly speaking, the images are the same. You can see the streaks which were observed experimentally, and there are some maximum still, some maximum due to the tail of the diffraction curve. So these horizontal streaks are more or less the same for all ORM or not ORM waves, and it can be easily understood because the crystal acts as a Fourier filter, because from this many plane wave components, only those can diffract which fulfills simply the Bragg law. That means this is the Fourier filter. X-ray standing wave, maybe the last minute. This is the slide from Juraj's talk. So here we have the standing wave, and the standing wave produces the fluorescence, and we can measure the fluorescent radiation, and depending on the energy of the fluorescent radiation, we can recognize if this fluorescent wave comes from the germanium atom or from the tellurium atom, because the fluorescent wavelengths are different. And here I simulated simply the Poynting vector in the material in the position of germanium and tellurium atoms for the ORM wave, as you can see. The difference, again, this is the angular deviation from the diffraction position, and the changes are very small. That means the ORM wave cannot produce a standing wave effect, and this, what Juraj showed, is in fact caused by the non-ORM wave component of the incoming beam, which is always present. That means, in fact, we have something like pump-probe experiment. The ORM wave makes the polling, and the non-ORM component in the incoming beam makes a standing wave, which makes the polling, which makes it possible to observe the polling effect. Okay, so summary. I have no time, so I can simply click, 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 click. So this is the summary of my talk. And finally, my acknowledgement, I would like to thank the Konstantin for a long Zoom discussion, which brought us to the idea. Without that, we would not move ahead. And organizing committee for travel support and our grant agency for some money. Thank you for your time.